In this lesson, we're going to begin our study of ionic bonding, one of the three major types of chemical bonding. Up until now, we've spent a lot of time talking about atoms, their structure, their electrons, and how we can predict their behavior from the periodic table. Now we're going to shift our focus slightly and ask a very important question. What happens when atoms interact with each other? For example, why does sodium react so dramatically with chlorine? Why do some elements form solids with very high melting points? And how can we predict the formulas of the compounds that they form? By the end of this lesson, you should be able to explain what an ionic bond is, identify cations and anions, and write correct chemical formulas for ionic compounds based on their charges. So as I said, there are three different types of bonding in chemistry, and it depends on what kind of elements you are mixing together. So for the ionic compounds, you are combining a metal and a nonmetal. For covalent, you are bonding together two nonmetals. And for metallic, it's going to be two metals. Now, whether metallic bonds actually exist or not, that is kind of up for debate, but we are going to say that when you're mixing metals together, you have some sort of an interaction going on. When nonmetals and metals combine together, they transfer electrons to form ionic bonds. Now, if you remember, metals have low ionization energies, and halogens in this case, for nonmetals, have high ionization energies. So that means if you put the two of them together, sodium, the metal, is going to lose its electron, and chlorine is going to accept it. So we have our electron dot diagrams here, and we're going to give it to the plus. And so now we're going to allow those electrons to transfer. And now we no longer have electrically neutral atoms, or ions actually. So sodium has lost one of its electrons. An electron has been subtracted from it. So it now has a +1 charge, and it's called a cation. Remember, electrons are backwards. So if you're subtracting electrons, you're going to end up with a positive charge. If you're adding electrons, you're going to end up with a negative charge. Which brings us to chlorine, which has gained an extra electron in the transfer, and now it has a -1 charge, and it's called an anion, kind of like onion, but with an A in front. So the properties, when you have ionically bonded solids, first off, they are almost always solids. There are some exceptions where they have ionic liquids, but they're kind of a special case. They're held together by very strong electrostatic forces holding them together. And it's because of those strong electrostatic forces that they have really high melting points. It's really hard to get the positive and negative charges unstuck from each other. They tend to be brittle, and that's because when you apply pressure to an ionic solid, what you're doing is you're pushing those positive, those like charges closer together. And they repel, and the solid would rather crack. Gives it a lower energy value than try to allow that to continue. And they make good electrolytes when dissolved in water. Not all ionic compounds will dissolve in water, but pretty much anything that forms ions in solution will be an electrolyte. So now we're going to look at how we can write formulas for them. So thinking back to the previous unit, we went over the common oxidation numbers. So you should get that periodic table out. So we saw that aluminum has a +3 charge when it is an ion. And then fluorine has a -1 charge when it's an anion. And so I'm going to use pictures first. And so aluminum is missing 3 electrons. So you can kind of think of it as being a square with 3 divots in it. So with these pictures, if you have something that looks like a rectangle, it is neutral. And if you have any kinds of divots or points, it is not neutral. And so fluorine has 1 extra electron, and so I showed that with a point. And so we're going to go ahead and allow them to stick together. Now the problem is that we still have 2 divots, so we still have some positive charge. So we're actually going to need 3 fluorines total in order to have this neutral compound. So if we wanted to write the formula for it, you can say, well, I got 1 aluminum and 3 fluorines, so therefore the formula would be AlF3. Now when you go to write formulas, there's a couple of things that people tend to do. You need to remember not to put a 1 if you only have one of them. By having that symbol there, you are saying that you have at least one of them. And so it's redundant to put a 1 after it. And people just don't do that. So do not put 1s, like in this case, after the aluminum. All right, so aluminum and oxygen. We already saw the aluminum is +3. Oxygen is in group 16, so that means it's going to be -2. Just needs 2 more electrons in order to get to that noble gas electron configuration. So there's our aluminum, and we're going to add the 1 oxygen. So we still have some positive charge, so we have to add another oxygen. Now we got too much negative charge, so we got to add another aluminum. So now we have too much positive charge again, so we're going to add another oxygen. We finally have our rectangle. Tells us that all of the charge has been neutralized. You can also add up the charges. So here we have a total of +6 from the 2 aluminum and a total of -6 from the 3 oxygen. So then we say, all right, well, we have 2 aluminum and 3 oxygen, so the formula would be Al2O3. Another thing that people do that's a little strange is they don't have these numbers as subscripts. They either put them in the same line or they have them up above because they say, well, they had numbers up above before. No, the numbers have to be subscripts because when you put them as subscripts, you are indicating to the reader that whatever that number is, it tells you how many you have of whatever's in front of it. So it says we have 2 aluminum and 3 oxygen per unit of this compound. And then we do aluminum and nitrogen. Aluminum is +3. Nitrogen is in group 15, so its common oxidation number is -3. You can see just looking at it, they already cancel each other out, so we know we're just going to need a 1-to-1. Notice that when you are writing formulas, and again we'll see why in a minute why this is really important to remember, we're always going to have the smallest whole number ratio. And that's because these ionic compounds don't exist as discrete little units where you have a single aluminum and a single nitrogen. They are crystals because they're ionic solids. This is what they form. And so we have like 1,000 aluminum and 1,000 nitrogen. And you can't write formulas for it like that. So the agreed upon convention is that we're going to have the simplest whole number ratio and reduce it down to the smallest possible unit that it can be. All right, so now we're going to try some. And so the first thing you have to do is you have to write down what the symbols are with their charges, or their common oxidation numbers. So sodium is in group 1, so it has a +1 charge. Chlorine, group 17, so it's -1. Now when you're in this technique, it's called crisscross most of the time. I've started calling it swap and drop because that seems to be a little bit more meaningful for my students. So the first thing you're going to do is you say, well, I never see pluses and minuses show up in formulas. Just think H2O. You don't see H +2O, like that. So we're going to throw the pluses and the minuses away. So they just disappear. And now we're going to swap the 2 numbers so they change places and then drop them down because they have to be subscripts. And so this, in essence, what you end up doing is you end up doing a crisscross with the numbers. Now remember, we don't show 1s because that's redundant, so we throw them away. And now we just kind of shove the letters together. So the formula for the compound that you get when you combine sodium and chlorine is NaCl, sodium chloride. Now let's do barium and chlorine. So barium is in group 2, so it's +2. Chlorine, we already saw, is -1. Throw away the pluses and the minuses. Now we're going to swap and drop. Get rid of that 1. So the formula, get rid of the 1. Doesn't like my clicking. So the formula would be barium, BaCl2. Calcium is also in group 2. Oxygen we saw in the previous slide, that's -2. So we can see that it is already canceling each other out. So it's just going to be CaO. If you like following a regular procedure, you can do the same thing. So we get rid of the charges, we swap them down. Now here's where you have to remember to simplify. That's one of the problems with just following the same recipe over and over again. We are not going to say it's just like with fractions. Let me turn my pen on. With fractions, and I'm just going to make up a number here, it's not proper to write down 2 to 4. You would simplify it down to 1 to 2. So in this case, we have a 2 to 2. That can be simplified, so it should be 1 to 1, but we don't show 1s. So we go ahead and you just do that. So gallium is under aluminum, so it's +3. Iodine is a halogen, so it's -1. So we do all the swapping and dropping, and we get GaI3. Indium is under aluminum, so it's also +3. Oxygen's -2. I'm just going to pause for just a minute, see if you can think of what the formula is going to be before I finish clicking. So then we throw away the plus and the minus, which people forget to do more often than you would believe. And then we do the swap and drop, and you get In2O3. And then aluminum and sulfur, it's not actually in the notes packet that goes with this anymore. I forgot to take it out. Aluminum's +3, sulfur is -2, and the reason why it's not in the notes packet anymore is because it is essentially the same thing as the previous question. So In2S3. All right, so now we got some more practice problems. So we have to say, all right, well, formulas for the following combinations. We have sodium and phosphorus. So sodium's in group 1. Phosphorus is -3. So you do the swap and drop, and you say that would be Na3P. Now we have magnesium is +2. Sulfur is -2. They're already charge balanced, so just BMGS. So carbon and silver, let me just say that metals are always positive. So that means the silver is going to have its +1 charge. And then carbon in this case will be -4. So we do that. And then we do the swap and drop. And we write the formula. And we see that it does matter which order that you put them in. Just because I put carbon first when I was setting up the problem doesn't mean it comes first in the formula. The cation always goes first in the formula. If you have trouble remembering whether things are cations, although it's the positive one, so I don't know, you could also say the metals always go first, and metals are always positive. Another way you can do it is you can say that it's kind of like reading a book. So we have silver, which is a transition metal, and then we have carbon over in group 14. So the carbon is more to the right on the periodic table, so that means it's going to be to the right in the formula. A whole bunch of different ways to think about it. So the next one, we have oxygen, -2. Zinc was another one that you were supposed to remember when we were going over the common oxidation numbers. That is +2. Cadmium is also +2. So they're already charge balanced, remembering that the positive one goes first, and you get ZNO. And then we have phosphorus, which is -3. Now, if you remember, I said that for the transition metals, other than silver, zinc, and cadmium, they can have a bunch of different oxidation numbers. And so what they used to do is they used to make you memorize a whole bunch of what the oxidation numbers were, and then you had to use these Latin-based terms for it. Like, for example, if somebody said ferrous something, you're supposed to know that meant that that was iron with a +2 charge. If they said ferric instead, that meant it was iron with a +3. There was no indication, just looking at it, what it was. There was a whole lot of memorization involved. So now what they do, something I'm very grateful for, is that they put a Roman numeral after the metal, the transition metal, to tell you what that oxidation number is. So this tells us that this is iron with a +2 charge. So then we put the metal first, do the swap and drop, and you get Fe3P2. All right, so some guided practice. There are some practice problems that go with this. I just have a screenshot of the two of them. And so I'm going to try to get out my little tablet pen, even though I'm not very good at it. So aluminum, we've already seen this one several times, is +3. Fluorine, it's a halogen, so it's -1. So you do the swap and drop, and you get, I'm going to have to erase that, AlF3. Now, this MM down here at the bottom stands for molar mass. It's like the next unit, we are going to be doing a great deal with this, and so I thought we would just start getting some practice with it now. So molar mass means you're going to add up the atomic masses of everything in the compound. So this compound has 1 aluminum and 3 fluorines. Whenever you say "and" in math speak, that means you're adding. So the atomic mass of aluminum is 26.982 grams per mole. That's the official unit. Plus 3 times fluorine, which is, I can never remember, 18.998. You do the math, and you get that the molar mass is equal to 83.976. Grams per mole. All right, so the next one, oh, that's not too bad. I thought I was going to be on top of it. So the next one, the reason why I picked this one is because it has that Roman numeral in there. There's a whole bunch of them on this particular sheet. So this tells us that we have scandium with a +3 charge. Oxygen is -2. So that means when we do the swap and drop, we get Sc2O3. So we're going to do 2 times scandium's atomic mass, not one I usually work with, so 44.956. Plus 3 times oxygen, 15.999. Oh, that reminds me, when we start doing a lot of this, you want to always keep at least 3 decimal places. If you start rounding off, the errors or round off errors in molar mass are going to contribute to some huge errors in what you're using it for. And so we do the math, and we get a molar mass of 137.909 grams per mole. All right, so that was it for sort of an introduction to ionic bonding. So one of the key things to remember from this is that you get an ionic bond when you transfer electrons from the metal to a nonmetal. When you lose electrons, you form cations. One of the ways I've heard of people remembering that cations are positive is that T has that little cross thing in it. So you can say, all right, well, there's my little plus. And then nonmetals gain electrons to form anions with the negative charge. Because opposites attract, you end up with these really strong electrostatic forces holding the ions together in a solid. Remember when you're writing formulas that you want to reduce if you're doing a swap and drop especially, you want to make sure that you have the simplest whole number ratio. So for example, whoops, I need the pen. If you were to write something like Mg4 O4, that can be simplified because you have 4 to 4. You don't want to have 4 to 4. So that should be just MgO. And then because of those electrostatic forces, ionic compounds have high melting points. It's very hard to get those ions so that they are free to move around and go into a liquid state. They're brittle and they will conduct electricity, they are electrolytes, if they dissolve in water. So that's it for this introduction to ionic bonding. Thanks for listening.